Question 2, okay? So what we have is a function, okay? So the function in question is x equals, okay. Well, okay. So what we have is we have displacement x, okay? So you're talking about a standard system where it undergoes simple harmonic motion, right? So you have a ball in the middle and it's going back and forth. Now, key thing to remember is that it's it's traveling forward and back, okay? So you have your okay, the full thing's grouped. No idea why. You have your ball here, okay? And this ball is going to go back and forth, okay? Using simple harmonic motion. Now, it starts off at an extremity. Can anybody tell me at t equals 0, how do I know it's at an extremity? How do I know it doesn't start in the middle? It's a cosine function, alright? So cos is at an extremity at the start, alright? So your displacement x is always your distance away from the centre. So x can be positive or negative, depending on how far you're away from the centre, okay? So x is always the distance back to the centre. So if I said, as an example, it's 5 meters from the wall to the halfway point, and I said, oh, you're 2 meters away from the wall, what's your x value? Your x value would be 3, because you're 3 meters away from the centre. Please remember, your x value is always referring back to the centre, okay? Now, your acceleration is always in the opposite direction to your displacement. That is very important for simple harmonic motion. So an example would be, if I am displaced by 2 meters to the right, so I'm 2 meters to the right of the centre, x is going in this direction. So x is a positive value. X equals 5 is going to the right. However, the acceleration is going to the left. Acceleration always in opposite direction to displacement every time. So you're going to go through your system. X equals 4 cos 2t. You might remember it from differentiation. If s is the distance, what's ds dt, or the first derivative? First derivative is velocity, and finally, second derivative, acceleration. So we're going to go through that here, okay? So, first one, dx dt, differentiate. When you differentiate cos, it turns into minus sign, 2t. The 4 is a constant, stays on the outside. Forgot one part. What part did I forget? Differentiate the angle to give you 2. First answer is minus 8 sine 2t. Everybody happy with that? Differentiate again. d2x dt squared. Your acceleration. Minus 8 is a constant, stays where it is. What does sine 2t change into? Cos 2t and then multiply by 2 equals minus 16 cos 2t. Now, this here, second derivative is your acceleration. A equals minus 16 cos 2t. Everybody happy with that? Now, what's going to happen next is that if you look at cos 2t at the very top, 4 cos 2t is equal to x. So by factorising out minus 4, you're going to get minus 4 times cos 2t. Happy enough with that? And minus 4 times 4 cos 2t is going to get me minus 4x. A equals minus 4x. A also equals minus omega squared x. You write a little note. Okay. Give it a second. Okay. Let's go back to this. And let's type in a note here. Okay. So, what you're going to notice is that it's since the acceleration is proportional to the displacement x and takes place in a opposite direction. How do I know it's in the opposite direction to x? Any sign does that for you? The minus sign. See the minus? So when a is positive, or sorry, when x is positive, a is negative. When x is negative, a is positive. They always go in different directions. Tom? I already did, but I'll link it in again. Basically, from simple harmonic motion, one of the preset formulas is a equals minus omega squared x. What I was showing is that the similarities between minus 4x and minus omega squared x, they're actually the same thing, but omega would be equal to 2, or omega squared equals 4. So I'm trying to say is that when we differentiate twice to get the acceleration, our acceleration formula here is consistent with the acceleration formula we've already used, that a is in the opposite direction to x at all times. So that's what I was about to get to on the right hand part here. So, and it's going to be in that takes place in the opposite direction to x. Okay, is that alright? You have to write that little note at the end. And you can also say, once you do this part here, see the a equals minus 4x, you can say simple harmonic motion with omega equal to 2. Is that alright? Now there's something else I want you to take into consideration now. When you set up a system, I want you to remember this, when you set up a system that's in equilibrium, so this point here is currently balanced by two forces, yeah? And this is the system that has omega equals 2. It doesn't matter how far you pull it away from the equilibrium. So if I pull it back 2 meters to here, it will go 2 meters to the left, 2 meters to the right. The omega value will still be 2. The only thing that changes, the further you pull it backwards, the bigger the amplitude. The omega value doesn't change. Is that alright? So when the system stays the same, or you still have the same strings pulling it, how far you pull it back doesn't matter. How far you pull it back only affects the amplitude. If you pull it back 2 meters away from the equilibrium point, your amplitude is 2 meters. If I pull it back 3 meters, it'll bob in between the two red zones here. So you're only affecting your amplitude, you don't affect the omega value by pulling it any further away from the equilibrium point. That will tie in the next exercise. Just want to hit it home now. Okay? So, what we're going to do next, guys, is we're going to what is the greatest distance between the particle and point P? Greatest distance, guys. What does that mean? Sorry?
V equals 0.
V equals 0. Okay, we'll think about this for a second. We start at an extremity, don't we? So we start at, because it's a cos, we start here, and this here is point P. Everybody agreed with that? Okay? What is the greatest distance between the particle and the point P? There'll be a position of equilibrium, and then it'll be over the other side, won't it? It'll be 2 amplitudes away. Would everybody agree with that? Amplitude here?
It's equilibrium. It's on one end of the equilibrium.
Because it's a cos function. Cos function starts at one end of the equilibrium. A sine function would have you starting dead centre.
Alright, okay.
So what do you think the answer there would be? I go for 2a. And it says greatest distance a equals 4 meters, right? So I'm just going to reread that. Greatest distance between the particle and the point B. Particle moves to displacement x in meters from point B after t seconds is given by this. Show that. Oh, sorry. This one here, guys. You don't. This one here is just talking about one direction only. So it's talking about how far you get away from P, and then how far you come back in towards it. So in a case like this, it's going to be the amplitude of 4 meters. The amplitude is the number that comes in front of the function. If that was 8 cos 3 theta, 3t, can anybody tell me the amplitude of that? 8. 16 cos 5t? 16, okay, so it's the number that comes in front of it. So The answer is the amplitude, which is 4 meters. Okay, so it can get 4 meters away in any direction. Now, how long will it take to go from a point where the velocity is 0 to a point 2.5 meters away from P? There's two sets of data there, guys, okay? So here's your sets of data. Okay, here's your data. So, you have how long is a time question from a point where the velocity is 0. Phi equals 0 is the first piece of information. You need to find the time. And then you also want to find when x equals 2.5, find the time. So you have two pieces of information here, yeah? Okay. So, the velocity is 0 at the extremities. Do you understand? So, velocity equals 0 at the extremities. So, let me reanalyze this. So, the clock starts, what we've already discussed, the clock starts at an extreme point, okay? In the graph where x equals 4 cos 2t, right? So this clock starts off at t equals 0 when you're at the extreme point. And now we're going to put in x equals 2.5. 2.5 equals 4 cos. Anybody? 4 cos? 2t. You're going to divide 2.5 by 4. And you're going to get cos 2t equals, what's 2.5 divided by 4?
5 over 8.
5 over 8. Cos inverse 5 over 8. Keep the answer in radians. I'm in degrees currently, am I? So shift, change, radians being number 4, and then we're going to cos inverse 5 over 4, or say 5 over 8, and what do we get there? 0.896. So 2t equals 0.896. Okay, and then divide it in half, and then t equals 0.4478. Okay, so if you imagine we started off, it goes, how long does it take to go from a point where the velocity is 0? Your velocity is 0 at an extreme point. When you start off the amplitude, you're just about to change direction, aren't you? So you start off at equals 0, then you're roughly from the equilibrium point, because you start off at an extreme point. How far away are you from the equilibrium point? We'll call this part the equilibrium point. How far are you away? If you start off at the amplitude, you're 4 meters away. Then you're going to travel, you want, and this is P here, okay, so you're going to travel 2.5 meters away, so x equals 2.5, and then you get your t equals 0.4478. Okay, we're good with that? We'll try another one out, guys. Very confusing at the start. I found this horribly confusing. Haven't done it in over a year, and just when you're getting back into it, it's tough. Let's try this one here. Does this start from the center or the extremity? Starts at the center, right? So, center is a particle moves so its distance x in meters from a fixed point O after t seconds is given by x equals 13 sine wt plus e. Now, the wt plus e, anybody? Yeah, the e is like a, what's that word? It's like a, it basically corrects it a little bit. It basically, in radian mode, it just moves the graph a little bit. So if you had a perfect graph like this, what the E does is it just sort of shifts the, sorry, let's rub this out for a second, we go again. What the E does is basically, if I draw an XY axis and I had a perfect one of these in mind, like that, sine function, what the E does is it can either shift it to the left or shift it to the right.
Like that.
Yeah, it just shifts it slightly along, okay? or it can occasionally, it'll actually shift up or down, right? It depends on what the E value is. Now, what we're going to do next, guys, is we're going to, with 13.t, t equals 0, x equals 5, okay? So, when t equals 0, x equals 5, how do you do that then? T equals 0, x equals 5. So, 5 equals 13 sine, anybody? Omega t plus e. Now, t being 0, if t is 0, the omega t basically isn't there. So, it's just basically sine e. So, sine e ends up to be 5 over 13. What's 5 over 13? Sorry? 5 over 13 is 0.3846 in radians. Oh, sorry, 0.3948 in radians.
Sir?
Yeah?
Why yours compared to radians?
So, guys, the E value, if you excuse me, the E value on its own, we sine inverse 5 over 13, so the E value here is going to be 0.3948. Okay, so 0.3948. The next thing it asks me is, can you find the value of W? Okay, so E equals 0.3948. Next thing we're going to do is find the value of W. Let's pay attention. We're going to find the value of W, okay? So, we know that phi equals 24 when t equals 0. So what's going to happen here is we're going to use phi squared equals omega squared a squared minus s or x squared, whichever one you want to use. I suppose we'll use x because x is down as the displacement in the question. Now that's done. This directly links the velocity information directly to the omega information. 24 squared equals omega squared. Now what's a squared, guys? What's a in this question? A? Remember I told you you get it from the function 13. And then x squared is x equals 5. Because we're told that at t equals 0, x equals 5, and at that point in time the velocity is also 24. So minus 5 squared. What's 24 to be squared? 576 equals 169 minus 25. 144 omega squared. Divide it, and you get omega squared equals 4. Omega equals 2.
Sorry.
Yeah?
Is that v squared formula, not the stack one?
That one there? Yeah, preset it. Yeah, it's in the log tables.
Yeah, the log table.
Yeah. Okay. The value of t when x equals 0 for the first time. The value of t when x equals 0 for the first time. Okay. So here's what's going to happen. You get your... Just while I'm here. What I've done here, guys, is I've compared two graphs to each other. The graphs I've compared to each other, if you listen, is x equals 13 sine 2t and x equals 13 sine t plus e, where the e value was 0.3948. On the graph here, you can see the regular one, which is the red one, that's the sine 2t. And when I put in the e value, what happened was, when you use a sine function, usually you start dead center, don't you, on the displacement. You usually start dead center. But by putting in this e value, what happened? I actually started 5 meters away from the equilibrium position. Do you got it? Because I started off at 0, 5. Then it asks you, when is the first time I hit 0? That's what the question asked, wasn't it? So you go up, back down again, and you hit 0 just below 1.4. Okay? How do we do that mathematically? Okay? So you hit it at 1.4 because of that e value. where you'd normally hit at 1.6 without the E value. Okay, so the E value obscured the graph a little bit. So here's what happens. We put down x equals 0 because your displacement is 0, and then the 13 now becomes irrelevant because the 13 is what was I going to say about that 13 again? The 13 is 13 times any number it's 13 times this number is 0, therefore the 13 doesn't matter. Sine inverse 0, anybody? 2t plus 0.3948 equals sine inverse 0. What's sine inverse 0? Huh? Sine inverse 0 in radian form, please. 0. Okay, 0 is one answer. So it can be either 0, it can be 180 degrees, which is pi, or it can be 2 pi. I can discount using 0. Can anybody tell me why I'm going to discount using 0? It'll come apparently obvious once you write down the formula. Time is negative. Can't happen. Discount 0. Okay, what about the next one? Pi. 2t equals pi minus 0.3948. And then to get t on its own, divide the answer by 2. What you get? Sorry, you get 2t equals
1.37.
1.37, yeah? Okay. And guys, as predicted, that 1.37, if you look at it on its diagram, you go back down, you hit 0 first at 1.37. Where would you next hit 0? At about 2.9. So if I was to use instead of using pi, if I use 2 pi to find the second time I hit 0, that's what answer I'd get out. Right. What we have here, guys, is we have and as an example, somebody please memorize this one off for me. See, x equals 8 cos 4t plus 6 sine 4t. Well, you just call those diagrams out individually for me in a second. So guys, here's what we're going to do. Will somebody call out the first part, please?
8 cos 4t.
Okay, y equals 8 cos 4t. And what you're going to notice here, guys, is that cancel. I don't want to create a slider. Invalid input. I don't think so. Oh, sorry, it's 4x. Now I remember. Okay, you can see that it's a bit on the. See the way it's a 4t, guys. 4t means that it's going to be oscillating. The peaks are going to come 4 times as regularly as they would in a normal graph. Okay, so that's why we have such a crowded graph there. So what I'm going to have to do is going to have to stretch this out a bit. That's 8 cos 4t. What's the other one?
6 sine 4t.
6 sine 4t. Now, you can see that the 6 hasn't got the same amplitude as the 8. And the 4t, the peaks are occurring just as regularly as each other, aren't they? The distance between peaks are the same. If you were to get a ruler out, definitely the same. Now, what happens in the resultant graph is constructive and destructive interference. So basically, you add together the heights that are above the ground. So you can see that this graph here, see this point here, see the way they're both roughly this much off the ground. This will result in a point twice as tall. Okay, so when we combine both of them together, we get y equals anybody? 8 cos 4x, and then plus 6 sine 4x, and look, you get 1. Yeah, plus, yeah? I just put down plus, it's okay. So guys, stop lads, see this? You add the heights together to get the height of the new wave. Now, if one of the graphs is above the x-axis and the other one's below the x-axis, they actually take away from each other to produce a point that's lower than one of the original graphs. So basically, you're just adding the y values together. So if I was to be really clinical about this here. Okay, to that. There we go. Okay, so if I go to this here, what happens is if you take any point, so an example would be this point here. See the way it's this much distance to there, and then it's a second distance from here to here. If you add both lines together, what you'll get is the distance to the newly formed graph. You're basically adding the y values together to form your new graph. Take any other point you want. Let's take this point here as an example. If I draw a line from this graph to this graph, it's that long. I draw a line from this graph to this graph, it's that long. If I add both y values together, it roughly produces the point of the new wave. Now that brings us back to the theory of the question we're just being asked, okay? The question's asking, how do you come up with a combined amplitude? Okay? So the new amplitude for any of these questions is just basically the number that comes in front of the cos, the number that comes in front of the sine, square them and add them together. So the amplitude of the new one is going to be 10. The period for the new one, period is always 2 pi over omega. In every case here, the omegas are always the same. You don't get two different omegas. 2 and 2, 4 and 4, 5 and 5, a half and a half. The omega values are always the same for both the sine and the cos function. Therefore, your period will be 2 pi over 4, which is the same thing as pi over 2. Is that alright? Okay.